disk like this, we need to integrate. So if you have some disk and it's at radius r like this, okay, and you're integrating over dr, so you're adding up all these little different radii of disks here. Okay, and this is one of many disks. Okay, the thickness of this disk is going to be dr. That's how thick the disk is. So the way I always imagine this is I cut the disk, I lay it out like this, and that makes a little strip. Okay? Now this is an area integral. I need to recast my area, dA, in terms of something useful. Okay? Well, what I need to do is I've got dq over dA, really, and I need to recast this little strip in terms of dA. Okay? Now, we already said that this side right here, that's the thickness of this disk, that's equal to dr. Okay? If I want to calculate the area of this little disk, it's dr, and what's the length of this side of the disk? 2 pi r. Okay? 2 pi r. That's the circumference of this disk, right? It's 2 pi r. So dA, that's the area, is going to be equal to 2 pi r times dr. That's the area of that disk. Then what you're doing, right, if this has a total charge q on it, okay, and you want to find what dq is for this, well, you have dq, that's going to be your eta, that's your charge density, that's going to be q over a, which is equal to q over the area of your disk, which is pi times big R, that's a radius of the disk squared. But really, what we need is this is going to be dq over dA. So in order to find the amount of charge dq on this disk, that's going to be dq over dA equals eta, and then we found what dA was in dq, so we get dq over dA, which is 2 pi r dr. And then from there you go ahead and solve for dq, so you get dq equals eta times 2 pi r dr, and that becomes your dq for a disk. Okay, that's probably the hardest part of setting up the disk integral, is just coming up with your dA, and then from there getting your dq. And it all, if you think about cutting this little strip and unrolling it and finding the area of it, that's how you go about doing that. So that's sort of an aside, but I would definitely go over that. Okay. Other things from this chapter. What does an electric field do to a dipole? If you put a dipole in an electric field, what does it do? It spins, right? It experiences a torque. So the torque on a dipole in an electric field is equal to P cross E. So in other words, if we have some, probably like a parallel plate like this, okay, you have an electric field, it's uniform, it looks like that, and if you have some dipole here, the positive side is going to be attracted to the negative side side is going to be attracted to the positive side, it is going to experience a torque, and here is P, that's our P vector, this is our E vector right here, this is the angle between them, theta, so you would get P times E times cosine theta. So that's how you would calculate the torque on a molecule in an electric field or a dipole. But it doesn't actually experience a net force. So it doesn't go to one side or the other in a uniform field, but it does, it's always attracted to a point charge. So if you put a dipole next to a point charge, it'll always be attracted to it. Yes?
Can we sign data for cross product?
Yeah, I think so. It should be. Thank you. And the reason why is because if you put it, here's your positive charge, here's your electric field, right? It's weaker over here than it is over here. First of all, it's going to orient the dipole in this direction like this. The negative charge is going to be attracted to the positive charge. The positive charge is going to be repelled. But since the negative charge is closer and it's in a stronger electric field, it's going to be attracted. So it's going to feel a net force in that direction. I might ask a conceptual question about that. How does a dipole move when it's next to a point charge, right? And the answer is it's attracted. And I might have you explain that, or something like that. It's good for conceptual questions. Same thing with the negative charge. If you replace this with a negative charge, this molecule would flip over and still be attracted. Okay. That's pretty much it for chapter 26. In chapter 27, we'll get as far as we can in the next 20 minutes or so. Chapter 27 is really all about Gauss's law. But we started off with the idea of flux, and that is if you have some surface like this, and you have electric field lines going through the surface, so that's your electric field like that, you have some area vector, and it's a vector that points perpendicular to the area, and it tells you something about the direction and the magnitude of the area. And you get that the flux through a surface is equal to E dot A, which is equal to E A cosine theta. So, in other words, the electric field, if it's pointing in the direction of A, that's the maximum flux. If it's pointing in the direction tangent to the surface or perpendicular to the A vector, then you have zero flux. And then the stronger the field or the bigger the area, the bigger the flux. Okay? So I might have you calculate the flux of a surface. I guess it would just be an exercise in math. But more importantly is Gauss's law. And Gauss's law is super powerful and it's fun to use, so you guys should use it. And what it says is that the flux through some closed surface is equal to the amount of charge enclosed over epsilon naught. This is a very powerful statement, and the whole reason why it's powerful is because you can use symmetry arguments to break this integral into a very easy integral or somewhat easy integral. Now, this can take several forms. One form would be I give you some geometric shape that you know, and then I say, here's the flux through each of these surfaces, how much charge is enclosed. That would be like the one manifestation of a Gauss's law problem. But more likely, you're going to have to find the charge of some enclosed charge density. So, and I would say that Gauss's law is pretty misunderstood by everybody so far. So let's talk about Gauss's law. So the first thing is that we need to choose a geometry for Gauss's law that works well. And the only way to do that is if the surface is perpendicular to the E field or the surface is parallel to the E field. So we need to pick some Gaussian surface that completely encloses our charge that matches those geometric constraints. If we don't do that, then we don't have much, right? And I can do an example for a line charge, a point charge, or a charge insulating sphere. What example would you guys like me to do? Charge sphere? Yeah. That's probably the best one. So you guys pretty much had this on your quiz, something like it. I'll go over that. We did a charge rod in class. A lot of these examples are going to be in your book. But let's go ahead and do this. So we have a charged insulating sphere. And the charged insulating sphere looks something like this. Okay. Now it has a charge Q distributed evenly throughout the whole sphere. Now if we do Gauss's law for the outside of the sphere, okay, well here's our charge. Let's say it's evenly distributed like this. And we do Gauss's law outside of the sphere. This has some radius, we'll call it big R, and this is our radius of our Gaussian sphere, I'll call it little r. Well, in that case, we do Gauss's law. Looks like this. So first thing we need to do is we need to think about the integral side, okay? And the integral side is always going to break down into something that we don't actually have to integrate. So you never have to integrate using Gauss's law, at least not for you guys. So in this case, if we look at the electric field for a sphere, it always points radially outward. So something like this, right? Be pointing in that direction, and it would be pointing in this direction, and it would be pointing in that direction. And then if we look at our little, this is the E field. And then if we look at our little area element here of our sphere, it's pointing out in that direction too. So we know two things about this. Since our Gaussian surface is a sphere and it's always equidistant away from our charged sphere, the electric field is going to be constant in magnitude, although it's not constant in direction. The other thing that we know is that A, that is our little area element here, and the electric field are always going to be pointing in the same direction. Over here, where it's pointing down, okay, our little area element is also going to be pointing in that same direction. So this turns into E dot dA, turns into well, it's E dot dA, that's E times A times cosine theta, and cosine theta for this is 0, so this just becomes the integral of E dA. All right, now the other thing was the electric field was constant over this whole surface that we're integrating, so we can pull E out because it's constant, right? Constant, at least in magnitude, E. So this gets pulled out. When we pull it out, we get E times the closed integral of dA. Now in this case, the closed loop integral of dA, that is the entire surface. So all we need to do is say, okay, well, I know what the surface of a sphere is. That is going to be 4 times pi times r. All right, so that is the integral. I have now taken care of the integral side of this equation right here. Let's go to the other side. So let's talk about, thank you, r squared. It's an area, it needs to be squared. All right, let's talk about Q enclosed. That's the amount of charge enclosed. And in this case, when our Gaussian surface is this big, how much charge is enclosed?
All of it.
All of it, right? So Q enclosed, in this case, is equal to Q. So I just say, okay, well, this is equal to Q over epsilon naught. I can go ahead and solve for E, and lo and behold, I get E equals 1 over 4 pi epsilon naught times Q over r squared. So I just rederived the electric field from a point charge using Gauss's law. Now that's because all of the charge was enclosed, but what happens if we have some Gaussian surface that's like this, okay? So that's inside the sphere. Well, then not all of the charge is enclosed. So the left-hand side of this equation looks the same. Left-hand side is E times 4 pi r squared. Okay, it stays the same as before. Everything is the same about the geometry. dA would be these little area elements right here. And E would be pointing radially outward still. Okay, so everything's the same. I'm sorry, all of these little A's should have been dA's. They're little tiny area elements. Okay, but the right-hand side is different. We need to figure out how much charge we enclose in our new Gaussian sphere. So this Gaussian sphere is less than big R. So first of all, we need to talk about our rho, which is our volume charge density. And that's going to be Q over V. Okay? Well, what's the volume of a sphere? Yeah, 4/3 pi r cubed. So this is really going to be Q over 4/3 pi big R cubed. Okay, that's how much charge is spread out evenly through our volume here. And that's what gives us our volume charge density, rho. Okay, now if I want to find out the amount of charge that's enclosed in our Gaussian surface, I go ahead and work this again. That's going to be, so this is V of big R. So in other words, V of the entire volume. I'm going to go ahead and rework this. I'm going to say, okay, well, for us, Q enclosed is going to be equal to rho, whatever that is. Well, I found that already, times my volume of my Gaussian surface. That's V sub little r. Okay, well, let's see here. We already said rho, that's equal to Q over 4/3 pi big R squared times, somebody say something? No. Okay. Times the volume of my little Gaussian surface sphere. And what's that going to be equal to? Yeah, 4